this is the best sentence. It's in the addendum. You got to. I have to read this sentence about our next speaker because this is just weird. Not weird, just amazing sentence. John Dubinski is a leader in the application of parallel supercomputing techniques to the stimulation of animation of galactic dynamics. John Dubinski.
Hi. Yeah. Okay. I love these Jupiter things here. They're really great. Okay. And this is a really great crowd of people, or a lot of great speakers today. A really tough act to follow, so I'll try my best. I've never spoken on one of these forums. My last venue was my daughter's kindergarten class. Okay. So I've modified my presentation slightly. Oh, okay, thank you. I'm an astronomer, and some people have called astronomy the world's second oldest profession. And so I'm a theoretical cosmologist at Toronto, and I write code, basically. That's my job. So my language of expression is C. So that's for all the techie code people out there. And so the things I do are simulating processes that form galaxies and structures, large-scale structures in the universe. Why am I here? Well, earlier this year, we did this big calculation, which I'd like to talk about, and I guess it made the papers, and that's why it attracted notice. And this calculation is the collision of two galaxies. Actually, to be fair, a lot of people are doing this, and I'm one of them. But what's neat about this calculation is it's the collision of our galaxy, the Milky Way, and this nearby neighbor, Andromeda. So it's sort of a look into the future. So there's been a lot of talk about the future of everything. This is a look 3 billion years into the future. So in some sense, human dimensions, it's really, you can't really imagine what's going on with humans in that far in the future. It's really a pure, well, it's really kind of like an intellectual wank, to be truthful. Okay. So you might wonder why the heck you would want to do something like that. Okay. So I thought I'd put it into sort of a historical, scientific context and bring you up to speed of why would anybody want to do such a ridiculous thing. Well, okay, so I thought I'd tell you about, Greek mythology. Andromeda, who's Andromeda, right? Well, in Greek mythology, right, Andromeda was this beautiful daughter of Cassiopeia and Cepheus, who were the king and queen, or the queen and king of Ethiopia, which is actually Palestine. Anyway, okay. Anyway, Cassiopeia boasted that her daughter was the most beautiful woman in the world, and even more beautiful than the sea nymphs, the Nereids. Now, the gods don't like hubris and arrogance. We don't know much about that here, I guess, in this venue. So Poseidon, who was, the sea nymphs were his daughters, was pissed off. And so he summoned this sea monster to wreak havoc on the coast. Okay. And so there was a lot of problems. And so the oracle said to King Cepheus, that, look, you've got to offer your daughter up as a sacrifice to this monster to stop this. So he complied. Okay. He's a good king. And so he chained his daughter to a rock, and she was left there to die, and be sacrificed to this monster. Meanwhile, remember this chained maiden idea. Okay, this is the shtick. Okay. Anyway, so the chained maiden. So she was chained to this rock, and so she's a constellation, by the way, Andromeda, and she's always depicted as this chained maiden. So anyway, meanwhile, Perseus was off on his adventures, and he came flying by on Pegasus, his friend, this flying horse, and he had the Gorgon's head, Medusa, which he had just killed. And this head is great because it can turn things into stone if you flash at them. So he saw this beautiful woman, was smitten, flashed the Gorgon's head, and turned the monster to rock. And so ends the story. And so they were married and had kids. Okay. One of their kids was Perses, who was the founder of the Persian Empire. Okay. According to legend. So anyway, where am I going with this? Okay. Well, so basically all of these characters, Andromeda, here they are on my shirt, actually. There's Andromeda, Perseus, Cassiopeia, Cepheus. They're all constellations up there in the sky. And in Andromeda, there's actually a galaxy, okay, which appears to the naked eye as sort of this elongated smudge of light, maybe a few times the diameter of the full moon. Okay, and so it's actually it's got an interesting historical, it's got a little story of its own. So the thing about this smudge of light, there was this Persian astronomer, a dervish named Al-Sufi in the 10th century who first noticed it, marked it on a chart, called it the little cloud. But when telescopes were invented, this little cloud, or nebula, as astronomers called them, turned out to be just one of many clouds, okay? And in fact, when people started looking around with telescopes, they saw tons of these things. And in fact, one of the interpretations, and Immanuel Kant was one of the first ones to make this interpretation, was that in fact what you were seeing was some kind of disk of light, a disk of stars, tilted at some angle. Because when you look at Andromeda, maybe I'll go to the slides now. Slides? Where will I go first? Okay, when you look at Andromeda, it is actually this sort of oval of light. But what it really is a big disk of stars. Next. Okay, there it is. Okay, so blew my story. Okay, so it's a galaxy. Okay, and so I don't want to go through the history of astronomy, but basically it became clear that eventually there was a realization that all of these things, these nebulae, are in fact big galaxies, aggregations of hundreds of billions of stars. And that, in fact, we live in a galaxy, the Milky Way. So that big arch of light you see across the night sky is the fact that we live inside of a disk. And so what you see is this big arch of light over the night sky. So back to Andromeda. So where am I going? So Andromeda is this galaxy. It's about 2 million light years away. Where did I go? All right. It also features commonly in popular mythology, okay? Star Trek. In fact, this is where I was first introduced to this galaxy, sadly. I spent my whole childhood watching TV. Okay, and my parietal lobe is actually filled with images of Scotty and Kirk, not, okay. So anyway, so what's interesting about Andromeda is, so there's this vision of these galaxies with billions of stars. There's 100 billion of them or so. They're all expanding away from us in this Big Bang explosion. But the thing about the Andromeda Galaxy is, unlike all the other galaxies, it's actually falling towards us. It has this unique characteristic that it's moving towards us. The speed is actually, it's about 120 kilometers per second. That sounds pretty fast, but it's only actually about 20 times faster than the space shuttle. But at a distance of but if you work it out, at a distance of about 2 million light years, and if you sort of take into account that it's going to accelerate as it falls in, the two galaxies, this galaxy is actually going to collide with the Milky Way in 3 billion years or so. So in fact, the Andromeda Galaxy has sort of been this sort of object that's been central to the development of astronomy and our idea of a big universe, but actually it's central to the destiny of the entire galaxy and actually even life on Earth. Okay? So what I'd like to do is take you through this calculation and then I'll show you a little movie that goes with it. All right. First of all, the idea of galaxies colliding is not really outrageous. We see in our local neighborhood maybe 1 out of 100 galaxies seem to be interacting. So this is an example taken with the Hubble Space Telescope. And in fact, something like this is going to happen to us. So here, now this is actually a simulated picture. Now imagine, okay, what I'm going to show you here is what will happen to our galaxy according to this calculation. Imagine flying for 1 million light years in this direction, which actually at this moment is the direction directly above the galaxy, okay? Turning around and then looking down. This is what you'd see, okay? And this is 3 billion years hence. So this galaxy here is the Milky Way, and this is Andromeda. This is about a couple of 100 million years just before they're going to collide. Now, I thought I'd also talk about how you can actually do these kind of calculations, because it's really advances in technology that allows you to play these games. What you do to do this kind of, I'll take you through it, but what you're doing is you're following the motion of roughly, in this case, 100 million particles representing stars in the two galaxies. Now, the motion of these particles is governed by the laws of gravity as defined by Newton. And so you use these big computers, and in this case, the way things are going now in supercomputing is you take many, many computers and sort of line them up in parallel, spread the job over all of those computers, and then just calculate the gravitational forces acting on each of those 100 million particles, and then following them step by step through a collision. Okay, and what's amazing about this is that all of the equations which describe this motion were actually written down by Newton 350 years ago. So it's only now that we can actually explore in really a complex way what goes on according to Newton's laws of gravity on this scale. I should point out that Einstein, you know about Einstein. He invented this other law of gravity, which superseded Newton's law. But in fact, Newton's law is perfectly fine for describing this kind of process. Okay? And only now are we beginning to be able to use it. Okay, so what happens? Okay, I'll go back. The Milky Way will swing by Andromeda on this side, okay? And the gravitational forces, turns out galactic disks are very delicate things. They don't like to be disks. And if you hit them with enough gravitational perturbations, they do beautiful things. And one of the things they do is they create beautiful spiral structures, okay? So you can see right after the interaction, both galaxies, now this is the Milky Way now, develop these beautiful bisymmetric spiral arms, as does Andromeda, okay? Things develop, and they throw off these big swaths of stars, and also there's a connecting bridge, and these things are commonly called tidal tails or tidal bridges in the jargon. And then the two galaxies fall back together and eventually merge. And after some sort of convulsive behavior, they merge. And they form a blob. They sort of transform into this single galaxy called an elliptical galaxy. Okay, this is the process. Okay, oops, I didn't want to show that. Okay, could you roll the first tape for me? So now I'll just show you the animation. So part of the big problem here in doing these kind of calculations is the data, because each frame of data requires several gigabytes. To save a couple thousand frames is impossible. So the images are actually rendered step by step during the simulation. Okay, so this is what's going on. So you can see beautiful spiral patterns develop it's very complex. And then the two galaxies fall back together in a very graceful, almost balletic choreography. Hey, how do you like that? And then there's this sort of orgasmic convulsion. I had to say something about sex. And then they settle down into this blob. And then you notice there's all these beautiful patterns of shells and ripples, sort of like the ripples in the pond after a big splash, which hang around for a while. But eventually they go away and erase, and then you form these sort of very regular-looking, smooth-looking things. And we see these kind of galaxies all over the place. Okay, so, okay, here it is again. This is just the close-up, so you can see what's going on. This is sort of like time-lapse photography. So essentially, This is a billion-year time scale. A billion years. That's a long time. Every second is about, what is it, 50 million years. So imagine, like, 1 second, the dinosaurs, 2 seconds, people, 3 seconds. I don't know. That's the time scale, and we're one of the stars in this big mess of action. Okay, so we sort of see the universe as a snapshot frozen in time, but actually it's very vibrant and dynamic, and there's a lot of things going on. Okay. All right. Thanks for the tape there. Let's see. Slides again. Okay. Here's just another shot. This is a shorter clip, but showing this is the Andromeda Galaxy, and it actually develops some really detailed, beautiful spiral patterns in its center. And if you look at, that's a better rendered version, but if you look at, there's real galaxies that look like this. Okay, so this is a famous galaxy in the northern sky called the Whirlpool Galaxy, which is more or less doing the same thing as what's going on in the simulation. Okay. Where did I want to go with this? Right. Here, I've been fooling around. I'm a dilettante in terms of computer graphics, and I've sort of been fooling around with virtual flybys, a virtual tour. So imagine you're flying in from intergalactic space towards one of these things. This is my attempt. I would love advice from the experts in the audience. Also, I'd like a soundtrack as well. So any musicians who want to make a contribution to my cause, I never get to talk to musicians. Okay. Right. And finally, oops. Okay, wait, I didn't want to show that. I'm really inexpert here. Could I roll the second tape? Now, I just want to put this in perspective. Like, okay, this is our two galaxies. They're doing their thing. But the whole universe is doing all kinds of stuff at the same time. So here is another piece of work that I've been working on, which is the simulation of clusters of galaxies. So galaxies actually, not only are they in pairs, but they also form in large groups. And here's a group of 100 galaxies which come together. And you can see the universe on this accelerated time scale. Here, 1 second is 300 million years. Okay, so in this case, it's like life, dinosaurs, humans, no life, sort of 1 second. You can see that there's this very complex behavior, dynamics. And this is all, again, just Newton, pure Newton. Pure Newton plus parallel supercomputers, okay? And some code, okay? And a lot of sort of staring at screens in the basement of my house, okay? And debugging. So, okay. And then this kind of picture is even, okay, that's okay with the tape there, is even a smaller part of even a bigger picture, right? Which is the whole universe. So you remember yesterday, Bart, who's my colleague, was showing you these pictures of this sort of cosmic microwave background fluctuations, this sort of fog of stuff with these little blobs in it. Well, those little blobs are the things that turn into galaxies and big structures. And so the theoretical side of what he's doing is trying to see how you can make the universe in a computer out of those little blobs. And so you try to make your universe the best you can, using these simulations, and people compare it to the real thing and go back and forth, and you try to find the right answer. Okay, that's sort of the process, scientific process. So go to the slides again. So I'll just show you one more. Oops, go to the next one. This is a universe in a box. Okay. So what do we have here? Well, here we begin with sort of the uniform Big Bang, where just right after that cosmic microwave background radiation forms. And then all of those little tiny fluctuations grow into these structures. I can play that again, I guess. They condense out of that fog. And so in this picture, each of these little specks that you see, those little condensations, is a galaxy, okay? And the big blobs are big clusters of galaxies, like I just showed you in the previous sort of picture, okay? So here, this is a volume hundreds of millions of light years across, okay? And you just get the big distribution of galaxies throughout space, okay? And so people like myself and tons of other people, so I don't want to take, I'm not like the originator of all this work, are working on trying to understand how these models of the universe can actually be compared to reality. And I'd just like to end my talk with a couple of images. I'm not used to talking about literary figures or things, but I'll do it anyway. Okay, so this is one of my favorite paintings by William Blake. Okay, I'm not a Blake scholar or anything, but from what I've read of his work and some stuff, he's sort of interesting character because he lived at the beginning of another technological revolution, which was the Industrial Revolution, and he kind of was anti-technology, anti-science a lot in his writings. And so this is sort of a pretentious painting, but it's a personification of his version of the sort of antagonistic Old Testament God, who he called your reason, okay? And your reason, it's sort of your reason, get it? Was a thing that sort of imposed rationality on the universe. And so his symbol of rationality was this, and science and technology was this compass, the Euclidean compass, this calculator. It's a computer at some level. And so I like the painting because it's sort of this idea that the universe, okay, it wasn't Blake's idea, but it's kind of, in the modern context, it's the idea that the universe somehow is computable. The sort of God or whatever who created the universe imposed laws which allow you to actually understand it computationally. And so just to end, more fun, another Blake painting, my second favorite one. Here's his picture of Isaac Newton computing naked, okay? Which I occasionally do as well. Okay, anyway, thank you very much.